So if there's no inert, then the concentration entering the reactor is the same as just the concentration of A that's in that inlet feed. And you see all I'm doing is just using that equation over there and substituting in theta I is equal to 0. And so what is that concentration? The flow divided by the volumetric flow rate. And because, another way that you can put this though is, what else is in this stream? Is there anything else in that stream, or is it pure A? So the concentration of A is also the total concentration of that stream, right? And so I can just use the ideal gas law in order to figure out the concentration of A within that stream. And so what do we get? We get Ca naught 1 is equal to that expression way over there. So 2 atmospheres, 1100 Kelvin, and we choose a gas constant that makes everything cancel. So 0.8206 liter atmosphere mole Kelvin. And you get with way more digits than are significant, and get that number in moles per liter. All right, so we haven't really set up the problem yet. We just took what they gave us and gave us something a little bit more useful. So what do we normally do to start one of these problems? What's the formula that we've always applied? Yeah?
Stoichiometry first?
Well, we usually put design equation first, but it's so simple that at this point you may just have written it off as being something you need to write out. But yeah, the design equation is just that equation for a PFR. Yeah, rate equation. So it does mention just in a single word that this is an elementary reaction. Okay? So what's the rate equation? Yeah, just the rate constant times the concentration of A. That's it. Now we have to put the concentration in terms of conversion in order to solve this differential. So that's where we come to the stoichiometry. And so if I put it now, I mean, I kind of already wrote some of this up there, but that's okay. Generally, the concentration of A is the flow rate of A divided by the volumetric flow rate, right? So what is the flow rate of A now written in terms of conversion? Yeah, you're a little ahead. The initial flow rate times 1 minus x. And now how do we deal with the volumetric flow rate? Is it constant? No, for multiple reasons, right? It's a gas phase reaction, delta is not equal to 0. And this isn't an isothermal reaction, so there's already going to be a temperature term in the volumetric flow rate expression. So what it actually looks like is the initial volumetric flow rate times 1 plus epsilon x times T over T naught. And I did go ahead and get rid of the P, I think it's P naught over P, yeah, because we are going to assume that the pressure drop is negligible. This is a PFR, not a PBR. So it's a safe assumption when you don't have a catalyst. Okay, so I can, what is this expression out front? Ca naught, right? And then you just get 1 minus x over 1 plus epsilon x. And we can make this a little bit neater and go ahead and invert the temperature ratio.
So pressure is constant for the whole reaction?
Yeah, we're going to assume that the pressure drop is negligible. Because there's no solid which the gases are flowing over, so it's a pretty safe assumption. And obviously this is an open vessel, so the flow in and out will change. Okay, so then what do we do? Combine, right? And so far, aside from leaving this in terms of, T naught over T, this problem is no different than any other problem you've done all semester. The fact that this is non-isothermal hasn't entered the equation. And so when we combine all of that, we get dx dv is equal to k times CA naught 1 minus x naught divided by FA naught 1 plus epsilon x times the derivative. This flow doesn't come from the stoichiometry term, it comes from the design equation. So that flow doesn't go away, even though the other one does. All right, just for a little bit more bookkeeping, what is epsilon?
Plus 1.
Generally, let's just YA naught times delta, right? And YA naught is what?
1.
1. Right now, it's 1. Remember, we're going to make this so that the inerts are no longer 0 in a second. So this is going to be one of the things we have to remember is going to change when we have an inert stream. It's not the only thing that'll change, but it will change. And then delta is what? 1, right? This is A goes to B plus C. So you're making 1 extra mole of product for every mole of reactant consumed. Okay, so epsilon is just therefore equal to 1. Remember though, when theta I is equal to 0. Okay, so now what's the other thing that we have to do? We have an equation where we have conversion as a function of, this is an ordinary differential equation with conversion on both sides. K is a function of temperature that I wrote out with the problem statement, and temperature is explicitly in my design equation. So, right. Let's also write out the energy balance. Okay, it's an adiabatic reactor with no shaft work. What else do we know about the reaction? Delta CP is 0. That guy's good at algebra. We know that because you take the products, which I've erased. It was 90 plus 80. The CP for A was 170. Not an accident. The book is nice. And again, for now, theta I is equal to 0. So if we take the general equation, which I didn't bring with me, and we substitute everything in, we want to solve for t as a function of x. It doesn't really matter that you do it that way. I think it's a little bit easier to set it up in Excel. So that's the one that I'm going to write out. And when you take all these things into account, you get negative delta H reaction times the conversion plus the heat capacity of A times the inlet temperature divided by the heat capacity of A. Now, if the inert wasn't 0, you would also have terms in here for the heat capacity of the inert. And I think I forgot to put that down, but I'm fairly certain that it's 200. I'll double check real quick. But we don't need it right now, but is it 200 somebody? Huh? But yeah, that term would show up along with theta I. But for now, theta I is 0, so that term isn't present. And of course, you can rewrite this in something that at least looks a little bit nicer. Okay, so we have two equations and two unknowns. But unlike before where we could use solver because they were both algebraic, even though they were nonlinear, you could still use solver. Now they're not. One's a differential equation, so we'll talk about the very easy to remember numerical method that's also easy to do in Excel. Okay, so if I'm looking at that essentially all we're going to do is take dx dv and replace it with what? Anybody remember?
X at plus delta.
I just like the notation v2, but you could do v1 plus delta v if you like that better. I think this is easier to kind of see. So we're going to take the conversion at some volume minus the conversion at some lesser volume. We're going to divide that by the difference between the two volumes. So each delta, we're literally just going to turn this mathematical operator delta into like a big Greek delta, meaning the difference between two things. And this is the Euler method, which is one of many for solving differential equations. It will work just fine for this course. So any questions about what we have before we, well, I'll write out the next two just so that you have it in your notes and it's clear before we get into the Excel part. So how do we deal with the rest of the problem? So K we were given as a function of temperature. What temperature do we want to use? Remember that we're trying to solve for the temperature as a function of its position along the reactor bed. That's going to depend on K, which is also a function of its position along the reactor bed because it's a function of temperature. So the point here is that you have to choose what temperature to use. We're going to use the temperature at, I guess if I'm using the same notation, the temperature that we put here to solve for K will be the temperature at V1. And so what is that equal to? So the problem statement told you that the temperature was the exponent of 34.34 divided by, and so this temperature is again the temperature at V1. And this equation is only valid if I use Kelvin as my units for my temperature.
What is T naught? The reference one?
T naught is